Welcome back. In this second lecture from section 15.7, we're going to do another example of the divergence theorem. Here we have a region bounded by a sphere of radius 2. The outward flux of the vector field F through the sphere is precisely the integral over the boundary of Q, that's our S, of F dot N ds. Right? It's expressed a little bit differently than the first example we did. We were only given the solid region, that is, the region bounded by the sphere. But if it's bounded by the sphere, that is the surface. Right? This is S, the sphere of radius 2 centered at the origin. We want to find the outward flux, that is the flux integral, through the sphere. Well, of course, the divergence theorem tells us that that's the triple integral over the interior of the sphere of the divergence of F dv. Well, let's not worry too much about Q for now. Let's write the triple integral. And then the divergence, the first component derivative with respect to x, the second component derivative with respect to y, and the third component derivative with respect to z. Now, we look at that x squared plus y squared plus z squared, and we're integrating over a sphere, right? That's our triple integral. I say integrate in spherical coordinates. Notice we're converting the triple integral to spherical coordinates. This now has nothing to do with the original flux integral, although if we were parameterizing the surface, we would probably also use spherical coordinates. But this is straight up. We're going to replace dv with rho squared sine phi, and then I will decide on the ordering of the differentials later, and then we'll have rho squared for x squared plus y squared plus z squared. And for a sphere, well, we'll have rho goes from 0 to 2, theta goes from 0 to 2 pi, and phi goes from 0 to pi. That's the whole sphere. So we would integrate from 0 to 2, from 0 to 2 pi, and from 0 to pi, and if we did it in that order, it would be d phi, d rho, or d theta, d rho. So there's what we have to evaluate. So from integrating with respect to phi, we're just going to get the integral of sine phi from 0 to pi. d phi, that's 2. You can work it out by hand. So we'll have a 2, integral from 0 to 2, integral from 0 to 2 pi. We have rho to the 4th, d theta, d rho. Well, there's no theta in here, so we're just going to end up multiplying by 2 pi. Integral of rho to the 4th from 0 to 2, and rho to the 5th over 5. You plug in 2 and you get 32 fifths. 32 times 4 is 128. So there we go. 128 pi over 5. Very simple integral, because we used spherical coordinates. Right? If you don't use spherical coordinates, you get something really horrible. If you try to do this in rectangular coordinates, then we're going to have from minus 2 to 2 in either the x or the y direction. Let's say it's the x direction. Y goes from 4 minus x squared, negative 4 minus x squared to positive 4 minus x squared. And z goes from negative square root of 4 minus x squared minus y squared to the square root of 4 minus x squared minus y squared. And then we have to integrate x squared plus y squared plus z squared. And this would be dz, dy, dx, z squared. That is a huge pain in the butt. So we're getting z cubed over 2 times x squared z plus y squared z. Then we have to substitute all of those radicals. So we'll have a term with the radical to the 3rd power, and 2 other terms, one with x squared, one with y squared, times the radical. Not pretty. Then you have to integrate that with respect to y. Yeah, don't do that. That is unnecessary. It is unnecessarily difficult. It's doable. All kinds of inverse trig function stuff and trig substitution stuff, but it is much easier to switch to spherical coordinates. The sooner you become comfortable with changing coordinates, the better off you will be doing these kinds of things. But that's pretty much it for the divergence theorem. There's not a whole lot else to explain. The divergence theorem tells you that two things are equal. If you can compute one easier than the other, use the divergence theorem to swap out the one for the other. And that's it for section 15.7.